Our next presenter is Catherine Lebel from the Department of Radiology at the University of Calgary. Catherine is a Tier 2 Canada Research Chair in Pediatric Neuroimaging who conducts interdisciplinary research using advanced magnetic resonance imaging, MRI, techniques to study brain maturation and how it is related to cognitive, behavioural and environmental factors. She is recognized for her foundational contributions to the understanding of brain development in typically developing children and those with neurodevelopmental disorders, such as fetal alcoholic spectrum disorder.
Hi, thanks for joining us. I'm really happy to be able to share some of my work with you today. The main focus of my research is to understand brain development in children, with the ultimate goal of supporting optimal development for each child. My research uses advanced magnetic resonance imaging, or MRI, techniques to study brain structure and function. I study children from infancy all the way through childhood and adolescence, and even into young adulthood. My research looks at how children's brains change with age, as well as how brain structure and function are related to different aspects of cognition, behavior, and a child's environment. This type of information is really important to inform diagnosis, intervention, and treatment for brain disorders, brain disease, and brain injury. It's necessary to have a good understanding of what is typical or healthy brain development in order to identify and understand what is atypical. Then, by understanding how the brain changes over time in both typically developing children and children with atypical conditions, we can highlight sensitive periods when the brain might be more susceptible to interventions. We can identify who might benefit the most from specific interventions, and we can determine which brain areas those interventions should target. It can sometimes be challenging to get good MRI data on young children. So my lab has worked really hard at the Alberta Children's Hospital to make MRI friendly for kids. We've made the MRI scanner look like a rocket ship, and we also have a mock MRI scanner where children can practice. To go along with the rocket ship scanner, we have a children's book about the experience that we share with families ahead of time so they can prepare with their kids. These types of techniques have helped my lab be quite successful in obtaining brain imaging on lots of young children, both those who are typically developing and those with neurodevelopmental disorders or risks for them. When children have an MRI scan, we collect lots of different types of information about their brains to measure both structure and function. For example, we can measure brain volume, thickness of the cortex, how well connected the brain is, and how coordinated function is across regions. One important aspect of my work is that we scan children multiple times and look at changes within individuals as well as between groups. This longitudinal data is critical to understand how the brain changes with age and to identify specific trends in more detail than when we look at differences simply across children. Early childhood is a really important time in development, when the brain grows very quickly and lots of new behaviors and cognitive abilities emerge. Yet we do not know a lot about how brain development during this time supports those emerging cognitive skills and behavior. Some of the work we do in my lab examines the early neurological roots of cognitive difficulties in children. For example, we've shown that alterations to brain structure and function are associated with pre-reading language skills in young children, even before reading begins. This suggests that the brain origins of reading difficulties begin early, before children have had formal reading instruction, rather than resulting from struggles with reading. Brain volume reaches about 80 to 90% of adult size by age 5 years. However, brain development doesn't end at this point, and there's a huge amount of maturation that happens after that time within the brain. Connections become stronger and more refined, while some regions become more specialized in their function. My work has looked in detail at how brain changes unfold throughout childhood and adolescence. We've been able to show that white matter, that's the brain's connectivity, continues to grow within individuals, even into the early 20s, and that development rates vary substantially across the brain. Furthermore, we've looked more specifically at the drivers of these white matter changes, highlighting some of the key processes underlying this development. In my lab, we also study how brain development is affected by the prenatal environment. Using neuroimaging, we've been able to show lasting changes to brain structure and function associated with prenatal alcohol exposure, including that brain development, how the brain changes with age, is different in children with prenatal alcohol exposure compared to children who are not exposed. This really highlights the lasting effects of prenatal exposure. It's not just a one-time insult, but it also changes how the brain grows over time. We also look at prenatal maternal mental health. Using neuroimaging, we've been able to show that brain structure is altered in children whose mothers had higher prenatal depressive symptoms. Prenatal depression is related to behavior problems in children, and our data suggests that one way in which this may occur is via alterations to the brain's connectivity. We recently launched a Canada-wide study of pregnancy during the COVID-19 pandemic, where we're following over 8,000 individuals through pregnancy, tracking their mental and physical health, life changes, and their infant's development. In Calgary, we're already looking at some of the babies' brains and seeing associations between brain structure in the infants and their mother's prenatal distress. As I move forward with this line of research, I'll continue to use advanced neuroimaging methods to understand brain development across infancy, childhood, and adolescence, as well as relationships between this development and cognitive skills, behavior, and the environment. With a better understanding of brain development, we can ensure that the right treatments are targeted to the right individuals at the right time, ultimately helping to maximize optimal development for all children. Thank you for listening.